Hello, I'm Ethan Coy.
And I'm Maddie Abrick.
Today we'll be presenting on the physics behind firearms.
So an introduction, today we're going to begin with a brief history of firearm development, the basic components that build a firearm and a bullet, and how it applies to physics and the barrel harmonics and its effect on accuracy, momentum conservation, and why we rifle gun barrels. So the history of firearms can date back to as early as 1250 AD and the development of gunpowder. Gunpowder was first created by combining elements such as charcoal and sulfur together to create an explosive element. They used gunpowder in the development of cannons to throw a projectile through the barrel. After seeing the success of cannons, muzzle loaders were created, which was the very first firearm. Muzzle loaders got its name because it was loaded from the muzzle. And muzzle loaders had three components: the barrel, the stock, and the igniter charge, which we will talk about later. After the development of muzzle loaders came matchlocks, which used a match to ignite the gunpowder to release the bullet. But as you can imagine, that was not very practical in war. So the flintlock was developed, which used the element flint to strike against the metal to ignite the gunpowder to release the bullet. After the success of flintlocks, rifling and sights came into play, and which led to what firearms we have today, which are self-contained cartridges, meaning that everything is contained in one unit. Rifles that you might be familiar with today that are self-contained cartridges are bolt-action rifles and semi-automatic rifles. This brief history came from the article, the NRA Museum article, A Brief History of Firearms. Over the past couple hundred years, firearms development and technology has advanced. However, the general physics behind firearms has stayed the same. So now we're going to talk about the basic components that build a firearm. First and foremost is the stock, which holds everything together. The safety, which toggles on and off to allow the action and firing pin to shoot. The action is what chambers the bullet and holds the firing assembly. The trigger is what strikes and releases the firing pin to release the bullet. The barrel is where the bullet travels and builds pressure and velocity. And the muzzle is where the bullet exits. And the basic components that build a bullet are the primer, the propellant, the bullet casing, and the bullet. The primer is where the firing pin strikes the bullet and lights the propellant inside. The propellant is the gunpowder, and when it is lit, explodes, causing gases to propel the bullet forward. The bullet is the projectile that is launched, and the bullet case holds all components of the bullet together. So now that we have a basic understanding of the history of firearms and how firearms work, our first topic on how it applies to physics is barrel harmonics. According to the Gun Digest article, Ballistics, Understanding Barrel Harmonics and Accuracy, quote, the manner in which a barrel whips, torques, and contorts is referred to as, quote, barrel harmonics, end quote. As you can see, the barrel is on a baseline. When the gunpowder is ignited, the bullet is released, which sends pressure waves down the barrel and back in a repeated motion, causing the barrel to move up and down from its baseline. This is important in physics because it relates to accuracy. Accuracy comes when the harmonics is repeatable. Consistency of the whip and torque are very important because you want the bullet to leave on the same level on the wavelength each time. Variables that affect the whip and torque of the barrel are the mass and length of the barrel, the bullet used, the gunpowder, the density, and size. This is important in shooting sports and things that require accuracy.
Next we'll be talking about momentum conservation in firearms. To start off, we'll talk about Newton's third law. So for every action there's an equal and opposite reaction. This is evident and can be seen in firearms, because when shot, the energy of the bullet changes from potential to kinetic. And because the bullet and the rifle are on a flat, linear line, we measure momentum in a linear scale, so we measure the linear momentum. And according to the University of Fairbanks, Alaska, This formula is the mass of the gun times the velocity of the gun is equal to the mass of the bullet times the velocity of the bullet in the opposite direction. So what this means is that when a gun is fired, the linear momentum of the gun will always be zero, therefore conserving momentum. So after looking at this, one might wonder, well, why does the bullet accelerate much faster than the gun? Well, this has to do with the mass of the gun compared to the mass of the bullet. So according to the University of Fairbanks, Alaska, the gun doesn't accelerate as fast because it has a lot more mass. And we can calculate acceleration by the acceleration is equal to force divided by mass. So for an example, if you had a gun that weighed 20 pounds and a gun that weighed 9 pounds, and they shot the same bullet, the gun that weighs 20 pounds will have a lot less felt recoil than the gun that weighs 9 pounds. Next we'll be talking about the physics of a rifle barrel. So rifling causes the bullet to spin, and therefore it stabilizes as it travels through the air. According to the American Physics Institute and their essay Analysis of Gun Barrel Rifling Twist, rifling is a number of spiral-shaped protrusions and grooves in the barrel. Its function is to give muzzle rotating speed to the projectile. So what this means is as the bullet travels through the barrel, the rifling and the barrel cause friction on each other, and it causes the bullet to spin. There are many different types of rifling. It depends on twist rate and how many grooves are notched in the barrel. Here we have an image of rifling on the left, and in this image you can see the lands and grooves that make up rifling. So why does the rifling and the spinning of the bullet stabilize it as it travels? Well, the spinning of the bullet creates a gyroscopic motion, which according to gyroscopes.org is a rotating wheel whose axis is free to turn but maintains a fixed direction unless acted on by an outside force. So this results in the bullet trying to keep its level axis as it spins, and as one side of the bullet comes around in the rotational motion, it'll keep a level axis and keep it from tumbling through the air. This is because Newton's law that states that an object in motion wants to stay in motion unless acted on by an outside force. So the spinning of the bullet paired with the forward inertia of the bullet keep it going straight and on a smooth path to where it needs to go. In conclusion, we talked about a basic history of firearms and their components. We also talked about how the barrel harmonics affect the accuracy and that the barrel whips, and in order to achieve optimal accuracy, you need that bullet to leave the barrel at the exact point on that transverse wave. We also talked about the momentum conservation in firearms, and that momentum in a firearm bullet system will always be zero because as the bullet leaves the gun, there's an equal and opposite force pushing the bullet forwards and an equal and opposite force pushing the gun backwards. And finally, we talked about how rifling of gun barrels makes guns more accurate because as the bullet travels through the air, the spinning stabilizes the bullet and keeps it from tumbling. Thank you. And this is our work site.